Yeah. For acids, it's just this. You just memorize it. Ides form the hydroic acid. And so what are all the ides? I mean, we could list all the ides. Fluoride, hydrofluoric acid. Chloride, hydrochloric acid. Bromide, hydrobromic acid. What else? Iodide, hydroiodic acid. Can you name any other ides for me?
Phosphoric.
I'm sorry?
Phosphoric.
Oh, that's an ick. I'm on one with I.
Sulfide.
Sulfide. Okay, what is sulfide's formula? Sulfide. Yes, did I write this down yesterday? Sulfide. Sulfite. Sulfate. Sulfate. Sulfite. Sulfide. The T means oxy, oxygen containing. D is usually monatomic. Usually monatomic, but not always. So sulfide is S2 minus, the acid, H2S. Hydro, sulfuric acid. Any other ides? You should be able to tell me all the ides that you know. There aren't that many. What other ides are there? Selenide, telluride, you know? Selenide. Selenide would be hydroselenic acid. Any other ides you know? Phosphide. P3 minus. What would that be called? H3P.
H3P. Phosphoric.
Phosphoric acid is H3PO4. H3P, it's the same pattern. This is why we're doing it. There's different ways of arranging it. It's going to be called hydrophosphoric acid. That's hydrophosphoric acid. Tell me all the ides you know. Have you started memorizing them? I'm missing some. Nitride. It would be called hydronitric acid. Well, hydronitric acid is not the common name for this. The common name for this is ammonia. Ammonia. But you could call ammonia hydronitric acid if you want, because we'd be following the rules. What else? Give me one more ide. Well, hydride is tricky because it'll form hydrogen gas.
Carbide?
Carbide, yeah. Carbide would form methane. You know, it's not a very good acid, but it would be hydrocarbonic acid. Oxide would be, hydroxyic acid. Hydroxyic acid would be AKA H2O, which is AKA water. So you want all kinds of fancy names for water. You could call water, or you could call water dihydrogen monoxide, or you could call water hydroxyic acid. If you called water hydroxyic acid, how many people would want to drink it? I have some pure hydroxyic acid for you. You want to drink it? Sure. Chemists would say sure, because they know that it's water. Right? Or dihydrogen monoxide, yeah, that's water. Hydroxyic acid, nobody calls it that, so chemists might not say, have to think about it. But we're just following the rules. But there's one more you should know, that this is a more common acid. Tell me an I that you have to memorize. You had to memorize hydroxide. But hydroxyic acid would just be water as well. You had to memorize peroxide, but we usually call it hydrogen peroxide. We don't necessarily call it hydroperoxic acid. You know, there are other names for those. But there is one that we do call by this name. What other I did you have to memorize? Cyanide. Cyanide. This is a common one. What would we call HCN? Well, there are two names for this. One name is when it's a gas. HCN gas is called hydrogen cyanide gas. Hydrogen cyanide gas. However, when it's aqueous, we give it the acid name usually. And the acid name for this would be, just follow the pattern. It's the exact same pattern for all these. What is it? Hydro cyanic acid. This is why people do all of them. People do all of them because then there's none left. And so when you do all of them, you see the pattern, none left, and then you should have the pattern or try to get the pattern down. You know, the more problems you see, especially with nomenclature, the better off you are. It's just not organized in this way. I should do the nomenclature that's just a lot easier. Everything's the same, so it just reinforces the pattern by repetition. And so these are the hydro-ics. Now, if you're doing ic acid, then it's got to be an 8. 8s make ic acids. So there are only 3 patterns for acids. So 3 patterns are if the anion ends in I, if the anion ends in 8, and if the anion ends in ite. And we'll have the 3 patterns for acids. For bases, the names are not so simple for bases, but not so difficult either. So let's look at a base. Like, let's take this acid, HCl, which is called hydrochloric acid, and we take a base. One base is sodium hydroxide. This is a base will counter the effect of the acid. And so, in other words, base can neutralize the acid. And so when this reacts, we have an interesting reaction take place in which the cations get swapped or the anions get swapped. So we'll have sodium chloride and water, H2O. And so what happens is this sodium hydroxide can neutralize the acid, forming table salt in water. So the base counters it. What is it that does it? It's the hydroxide. The hydroxide is the base here. The acid is the H+. And so when the H+ combines with the hydroxide, do you know what's formed? This is the acid part of this. This is the base part of this. And so when the acid reacts with the base, you know what's formed? Well, what's formed is water. Hydrogen ion and hydroxide ion are going to produce water, H2O liquid. If I did this with hydronium, hydronium just means a little bit more work. If I did this with hydronium, because I know hydrogen ion, what do you know about hydrogen ion? Hydrogen ions are too reactive, they're too unstable to exist in water. And so the hydrogen ions, when you see hydrogen ion, you think mentally, you think hydronium. And then if you have hydronium, it's the same reaction here, except when hydronium reacts with hydroxide, instead of forming one water, we form 2 waters. We have to balance things out. And so the base will neutralize acids. And so what are the bases like that? Strong bases, we know. We'll talk about the weak bases. Weak bases we've been looking at on charts. Well, these hydroxides have other chemical properties too. Hydroxides will dissolve fats. Did you know that? Hydroxides will will dissolve fats. They use hydroxides to make soaps, that kind of stuff. The soaps, you know what soaps are made out of? Like the old-fashioned way of making soap is you just take like potassium hydroxide, potash, and mix it with fat. And, hydroxide dissolves the fat. The product you get from that is soap. So hydroxides are used for other things too. I mean, neutralizing acid. So antacid. You know, milk of magnesia. Milk of magnesia is an antacid. And so it just helps neutralize your stomach acid. You know what it's made out of? Milk of magnesia? What's this called? Magnesium hydroxide. So let's say your stomach's upset. Let's say you use milk of magnesia, but you're all out. Let's say you look in the medicine cabinet, there's no more milk of magnesia, but you look under the sink and there's some drain cleaner. And then you realize, hey, drain cleaner, which is lye, is drain cleaner, is sodium hydroxide. So you go, hey, I ran out of magnesium hydroxide, but I have some sodium hydroxide under the sink. I'm going to just take the sodium hydroxide instead of the magnesium hydroxide. Why or why not? Why? Yeah, why? Because they're both hydroxides, they're both bases, they're both going to neutralize my stomach acid. And so why not then? If you ran out of milk of magnesia, just grab the drain cleaner from under the sink and use that to neutralize your stomach acid. Would you do it?
Sodium is a lot stronger than magnesium.
Why is it stronger? Wouldn't magnesium has 2 hydroxides for every magnesium. Sodium only has 1 hydroxide for every sodium. Why isn't magnesium hydroxide stronger? It's got 2 versus 1. Is that relevant? Well, maybe not so relevant, but it depends on how much you take. It has to do with the charge, yes, it does. So tell me more, Adam.
Is that because sodium would break apart from the hydroxide a lot easier, causing a more violent reaction?
Exactly. Yeah, that's exactly the reason why. In fact, it's this. Sodium hydroxide is what we call a strong base. Magnesium hydroxide is what we call a weak base. Why is magnesium hydroxide considered a weak base and sodium hydroxide considered a strong base? It won't break apart. In fact, this hydroxide is what we call insoluble. This one is soluble. Remember, the soluble hydroxides are the group 1, ammonium, calcium, strontium, barium. Magnesium is not on that list of soluble hydroxides. Magnesium hydroxide is insoluble. When you drink the stuff, it's a paste. It tastes pasty because you're drinking solid particles of magnesium hydroxide. Solid particles of magnesium hydroxide are going to be a lot less reactive than sodium hydroxide, in which the hydroxides are totally free. And so the first thing is you have to break the hydroxides free from the magnesium, which is not easy to do because magnesium is pretty high charge, therefore wants to stick. And so it's a lot less reactive. This is going to be a lot less reactive. You can drink this stuff, but if you were to drink this stuff, you're going to die. This is poison. whereas this people drink. It has to do with solubility. Barium, you know, I told you barium, remember barium chloride? We used that. I told you you gotta watch out for barium chloride because it is toxic. But do you know people drink barium sulfate? People who go in for CAT scans drink barium sulfate. How can they drink barium sulfate but not drink barium chloride? Let's say you let's say you're there, you know why they use it for CAT scans? Because barium's a heavy metal. Heavy metals absorb lead. And so, like, you don't want to drink a lead cocktail, but you can drink a barium cocktail. Lead's, I guess, more toxic. But heavy metals absorb lead, like lead absorbs lead, not lead, absorbs X-rays, sorry. Heavy metals absorb X-rays. And so they use barium sulfate for imaging, you know, because if you go in for a CAT scan, they shine X-rays at you and they want to image, like your whatever. And so let's say you ran out of barium sulfate, but there's some barium chloride. Would you use the barium chloride instead of barium sulfate? No, absolutely not, because barium sulfate is, well, sulfates are all what? Soluble except for silver, lead, mercury, calcium, strontium, and barium. So barium sulfate's insoluble. So if you drink this stuff, it's not releasing a whole bunch of barium to kill you. Whereas if you drink barium chloride, well, you get a lot of barium ions. So they're aggressively going to attack whatever they do. It'll elevate your blood barium levels. Okay, so solubility has lots of application. I mean, this whole thing, conceptually, you know, it's like, okay, you have two things. One, you could just memorize these things, but there's too much stuff to memorize. So you try to look for patterns and you try to understand things at different levels so that if you aren't given something you've seen before, you know, you might be able to infer, or you might be able to figure out something like this. I mean, this is very similar to the EDTA, you know. Sodium EDTA versus calcium EDTA, which one's going to be a better drain cleaner? The sodium EDTA is going to be a better drain cleaner, but do you want to use a better drain cleaner on a child? You know, that's what I think, you know, when I'm thinking about that. I'm thinking you have a choice of calcium EDTA or sodium EDTA. And me, drain cleaner versus milk of magnesia. To a lot of people, it doesn't make any difference, you know. To a lot of people, they say it's the same thing. But those people don't know chemistry, or not chemistry. Okay, we'll continue here where we were leaving. All right, so sulfuric acid is a strong acid, and so what it does is it completely hydrolyzes, in this case, so from hydronium and this one. But only one hydrogen comes off at a time. And so what we're going to be left with is one hydrogen, or one proton still stuck on the sulfate. So we have HSO4 minus, which is called, this 4 is supposed to be superscripted. It's HSO4 subscript 4 superscript minus. So there's one more, but HSO4 minus would undergo second step, but the problem is HSO4 minus is not one of the 7 common strong acids. So if it's not one of the 7 common strong acids, that means bisulfate is a weak acid. If it's a weak acid, then weak acids only partially ionize or partially hydrolyze. And to show that, this is what they were trying to show there, but it didn't come out on the slide. What they're trying to show is that it's going to be a 2-step process for H2SO4. So H2SO4, in the first step, I'm going to do ionization rather than hydrolysis. So I'm just going to go H plus HSO4 minus. That's it. In the second step, the second hydrogen breaks off. So we have HSO4 minus, and we'll get H plus and SO4 2 minus. But this is a weak acid. And weak acids only partially hydrolyze or partially ionize. So what we're going to do is we're going to show two arrows like this, showing it's not complete. This first arrow shows it's complete. The second, with the double arrow, shows it's incomplete. And so if I have a solution, let's have a beaker that's labeled H2SO4. If I have a beaker that's labeled H2SO4, I'm going to expect no molecules. And so H2SO4 molecules are 0. No H2SO4 molecules. In fact, I'm going to find mainly H plus and HSO4 minus. These are the main species. And then the HSO4 minus undergoes a little bit further. And so I'll expect another H plus and an SO4 2 minus. These are minor species. Minor species. And so the main species here is incomplete. It didn't completely dissociate. We have two hydrogens. It's diprotic acid. Only one of the hydrogens really broke off. The second one doesn't break off completely. So there's additional species there. Let's go on to the next one. The next one is this. This is called acetic acid, we saw earlier. Acetic acid, is it one of the 7 common strong acids? No, this is a weak acid. If it's a weak acid, then it doesn't ionize completely, so it just partially ionizes. And so what I'll see here is if I have a beaker of this and it's labeled acetic acid, what I expect to find in this beaker is mostly acetic acid molecules. This is the major species. And then some of those molecules will break apart into H plus and acetate. These would be the minor species. So that's why the double arrow here. Here they're showing we're going to use the shorthand. You know, they have this. Let's see, what are they doing here? This is kind of ridiculous. This second one. So here's the hydrolysis, here's the ionization reaction. The arrow got screwed up. The second one, the H plus is not going to break off the hydronium the other way. So when we're dealing with solutions, we want to look, what is the major species present? Minor species are going to be of less importance than the major species. The major species are 0. But still, we want to know. So we can see HCl. Is this HCl? Yeah. HCl. The major species are all the ions. Acetic acid, the major species are the molecules. And the minor species in acetic acid are the ions. There are no molecules in HCl. All the molecules have been dissociated. So there's going to be a huge difference in the quantity of ions. You know, it's just the minor species that are conducting. The major species don't conduct. Here for acetic acid. So let's look at the strength of the acid. More than half the molecules of a strong acid are ionized. So, you know, greater than 50% ionization. We'll just say complete ionization for strong acids. more than half the molecules in a weak acid are in molecular form. So it turns out hydrochloric acid is strong. Hydrofluoric acid is a weak acid. It's odd, you know, because hydrobromic, hydrochloric, hydroiodic are all strong, but hydrofluoric is weak. If we look at the percent ionization, in 0.01, this capital M means the concentration. It stands for molarity. So in 0.01 molar, it's 99+% ionized. The higher the concentration, the percent ionization goes down. So in 0.10 molar HCl, I'll talk about molar later. In 0.10 molar HCl, it's 79% ionized. That means 21% unionized. So 21% molecules, 79% ions. If we look at acetic acid, the numbers are a lot smaller. It's mostly molecules. So 22% ionized means 78% unionized molecules. And this would be 90.4% molecules. Okay, are we out of time?